In this video, we're going to complete the KutaSoftware Infinite Algebra 2 free worksheet function inverses. Our directions on this first part are to state if the given functions are inverses. And remember that if two functions are inverses, then if we were to plug x into one function and that results in some y, then we should be able to plug that y into the inverse of that function and get back x. And that's an easy way to check if two functions are inverses. So let's dive into number 1, seeing if these two functions are indeed inverses of one another. So again, if I were to plug some x value into this first function, I'm going to get the function value. If I take that function value and then plug that in for x in my new function, well, then I should get my original x as that output. If I plug in x and get y, then I'm going to use y to plug in for x, and I should get back that original x. I think doing an example of this will help solidify the concept. So let's set x equal to 0. If I were to plug x equal to 0 in for g of x, g of 0 is going to equal what? Well, plugging 0 in, why did I choose that? It's going to give me an easy problem. It's just going to give me a result of 4. So g of 0 equals 4. Now I'm going to see what f of 4 equals. And if f of 4, if that equals 0, that original x that I input into my first function, then I know these functions are inverses. If it doesn't, these functions are not. So let's see what happens when I plug in f of 4. Plugging 4 in for x, I'm going to get 1/2 times 4 plus 3 halves. This is going to equal, well, 1/2 times 4 is 2. 2 plus 3 halves, we know that does not equal 0. Therefore, the answer in number 1 is no. These are not inverses of one another. So let's check this out in number 2. In number 2, again, let's pick a point. And an easy point to pick for the first is a value of 0, because I can recognize that it's not going to cause any domain issues since both variables are in my numerator. I'm never going to get a divide by 0, so let's just choose n equal to 0. So g of 0 equals what? G of 0, plugging 0 in for n, we'll get negative 12 over 3, which is a negative 4. So g of 0 equals negative 4. I'm going to take this negative 4 and plug it in for n in my new function, f of n. So f of negative 4, what does that equal? If that equals 0, what I originally input into my first function, then I know these are inverses. If it doesn't, well then no, these are not inverses. So f of negative 4, plugging negative 4 in for n, we're going to have negative 5 plus 6 times negative 4 all over 5. That's equal to negative 5 minus 24 all over 5. Negative 5 minus 24 is a negative 29 over 5. That does not equal 0. So because that does not equal 0, I know that no, g of n and f of n are not inverses of one another. Let's move on to number 3. In number 3, we have f of n equals negative 16 plus n over 4, and g of n equals 4n plus 16. If we want to see if these are inverses of one another, let's set n equal to 0 at the start. So we're going to take f of n and plug in 0 for n. So f of 0 equals negative 16 plus 0 over 4. Negative 16 over 4 is simply negative 4. Now what am I going to do? I'm going to take this negative 4 and plug it into my other function. So the output of my first function, when I plug that in as the input of my second function, or the function in question, to see if it is indeed an inverse, I should get the original input into that first function. So I know that's a lot, but we're taking this negative 4 and plugging it in for n in our second function. So g of negative 4. If that equals the input to our first function, then we know they're inverses of one another. So plugging in negative 4, I'm going to have 4 times negative 4 plus 16. 4 times negative 4 that's a negative 16 plus 16, that equals 0. So it does indeed equal this original input. So yes, in number 3, these are inverses of one another. And another good thing to do to double check if they're inverses is, well, think about how to solve for an inverse. The first step in solving for an inverse is you switch the input and the output, essentially switching x and y. So I'm going to rewrite f of n equals negative 16 plus n over 4 as y equals negative 16 plus x over 4. Now what I want to do to find the inverse function is I switch my x and y. All I'm doing is replacing y with x and x with y. Now, in order to find the inverse of this function, I solve for y. So in solving for y, I multiply both sides by 4 to get that 4x equals negative 16 plus y. And then I move my negative 16 the other side by adding it. So I'll get that 4x plus 16 equals y. What does this look like? It looks like this inverse function right here. G of n, my y, equals 4n plus 16. So this is going to be useful when we go into our next steps in our worksheet, how to actually solve for those inverse functions. But for now, let's just keep plugging different numbers in. So again, an easy number to plug in is 0. And I'm choosing 0 because it makes the math simpler. You can choose any input value for that variable, but 0 is always easy to work with. So f of 0 is going to be equal to, plugging in 0 cancels out that first term, it's just negative 16 over 7. So now what I'm going to do is I'm going to take this negative 16 over 7 and put it into my input into my second function. So g of negative 16 over 7, I have to see, does that equal what? Does it equal the original input of 0? So g of negative 16 over 7, we're going to have 3 halves times negative 16 over 7 minus 3 halves. Now it's obvious to see that if this was a 1, 3 halves minus 3 halves would give me 0. Negative 16 over 7 is not a 1, so I know I'm not going to get 0 back, but let's just work through the math just a little bit more to show you that I will not get 0 as my result. So simplifying this down, we can take this 16 and 2 and turn it into an 8 over 1. So then we have 3 times 8, which is 24 over 7 minus 3 halves. Now in order to simplify this down, I need a common denominator since I'm subtracting fractions. So the easiest way to find that common denominator is just to multiply by the other denominator. So 7 is going to get multiplied by 2, and 2 is going to get multiplied by 7, but I need to always multiply by the number 1 so that I don't change the value of my overall function. So 7 over 7 and 2 over 2. So this is going to give me 2 times 24 is 48 over 14. 3 times 7 is 21 over 2 times 7 is 14. Subtracting those, you can see that I over 14, which again is not equal to 0. Therefore, no, these are not inverses of one another. Moving on to number 5. Again, let's choose that point of 0. So f of 0 equals negative 0 plus 1 cubed. So negative 0 plus 1 is going to be a negative 1 cubed, which results in a negative 1. So if that's my output for plugging in 0, I'm going to take that output and plug it in to my new function. So negative 1 now is getting plugged in for in my function for g. So g of negative 1 equals 3 plus negative 1 cubed. Negative 1 cubed is a negative 1. 3 plus a negative 1 is a positive 2. You can see that this value 2 does not equal my value of 0. Therefore, no, these are not inverses. Moving on to number 6, let's start by plugging in n equal to 0. So f of 0 is going to give me 2 times negative 2 cubed. Negative 2 cubed is going to result in a negative 8, and 2 times negative 8 is going to give me a negative 16. So now what I'm going to do is I'm going to take that negative 16 and plug it in for in my function g. So g of negative 16 is going to equal 4 plus the cube root of 4 times negative 16 all over 2. What's that equal to? That's going to be 4 plus 4 times negative 16 gives us a negative 64. And the cube root of that is a negative 4. So we have 4 plus negative 4 all over 2. 4 plus negative 4 is 0, and 0 divided by 2 equals 0. So look, we got 0 as the output of g of negative 16, and our original input was 0. Therefore, for number 6, yes, these are indeed inverses of one another. And just to be sure, let's confirm this by taking the inverse of a function. Last time we took the inverse of f of n, let's go ahead and take the inverse of g of n and see if we get our original function f of n. Again, how do we take the inverse? We start by writing our function normally, but I'm just going to write it in terms of x and y as opposed to in g of n. So I'm going to have y equal to 4 plus the cube root of 4x all over 2. In order to find the inverse function is to switch our x and y. So y is going to become x and x is going to become y. So I have that x equals 4 plus the cube root of 4 times y all over 2. Now it's just a matter of solving for y. When we solve for y, that is the inverse function. So I'm going to start by multiplying both sides by 2 to get 2x equals 4 plus the cube root of 4y. Now, when I subtract 4 from both sides, I'll get that 2x minus 4 equals the cube root of 4y. In order to isolate y, I'm going to need to cube both sides. So I'm going to get that 2x minus 4 cubed equals 4y, because the cube root will cancel out with that exponent of 3. Now my last and final step is just to simply divide by 4. So I'm going to have 2x minus 4 cubed all over 4 equals y. Is that my original function f of n? It doesn't actually look like it, so let's see if we can manipulate this to make it look like 2 times n minus 2 cubed. And let's think about it. 2x minus 4, how can we break this up? Well, there's a common factor of 2 in both of my terms. So I'm going to rewrite 2x minus 4 as 2 times x minus 2. But remember, this entire quantity is cubed, and that's all over 4 equals y. So all I did here was I saw that 2 was a factor of both my terms within my parentheses, but I can't necessarily pull it out in front because of this cube, so I just wrote it still within those parentheses so I know that it's still cubed, but now I have multiplication, so I can distribute this cube to x minus 2 and to 2. So we're going to have 2 cubed times x minus 2 cubed all over 4 equals y. So this is looking very similar because now I have my n minus 2 or my x minus 2 cubed. I just need to finish simplifying down. 2 cubed, what is that? Well, that's really 8. So if 2 cubed equals 8 and I have 8 over 4, 8 divided by 4 is 2. So there we have it. I've simplified this down so that we have 2 times x minus 2 cubed equals y, or in our case, 2 times n minus 2 cubed equals f of n. Let's move on to number 7. Now that we have confirmed that number 6 are indeed inverses. In number 7, I can plug in a 0 for x. It's not going to be undefined since we are subtracting 2. We're not going to have 0 in the denominator. So f of 0 is going to be equal to 4 divided by negative 2, which is a negative 2 plus 2. Negative 2 plus 2 equals 0. So we just need to plug in 0 now for h of x and see if we still get out 0. So h of 0 equals negative 1 over 0 plus 3. That equals a negative 1/3, which does not equal 0. Therefore, no, these functions are not inverses of one another. Moving right along to number 8, what are we going to plug in? Well, here's a case where we can't plug in 0 because then we're going to be dividing by 0, which is undefined. So we're going to plug in, let's plug in another easy number. Let's plug in 1. So g of 1 equals negative 2 over 1, which is a negative 2, and then we're subtracting 1. So this is going to give us a negative 3. Now we're going to take this negative 3 and plug it in to our other function. So f of negative 3, if we do indeed get a positive 1, then we know that these functions are inverses. So negative 2 over negative 3 plus 1, that's going to be a negative 2 over, well, negative 3 plus 1 is a negative 2. Negative 2 over negative 2 is a positive 1. We got back that original input, so yes, these are inverses. And we can confirm by solving for the inverse function of one of them to see if it gives us the other. But we're going to get lots of practice with that down below. So let's move on to our next set of directions. For this next set of directions, we're going to find the inverse of each function. So starting off with number 9, what are we going to do? Well, I like to write it in terms of y equals some expression with x. So I'm going to write this as y equals the cube root of x minus 3. Our first step after we rewrite is to switch x and y. So we're going to have x equals the cube root of y minus 3. Now it's just a matter of solving for y. Once we solve for y, we have our inverse function. So we need to start by adding 3 to both sides. So we get x plus 3 equals the cube root of y. And then, in order to isolate y, we just need to cube both sides. So we get that y is equal to, since the cube root cubed will cancel out, that's equal to x plus 3 cubed. But I want this in function notation. X was indeed my input, so I'll leave x as is, but y I will now write as the inverse of h of x. So the inverse of h of x equals x plus 3 cubed. If we were to leave it as this, well, I know that this is the inverse function, but it's not in proper notation. So we would need to write it as the inverse of h of x equals x plus 3 cubed. Let's move on to number 10. In number 10, we have that g of x equals 1 over x minus 2. As opposed to writing this in terms of x and y, I'm going to swap my g of x and x, but I'm going to make note that by swapping that, it's really the inverse function. So I'm going to have x equal to 1 over the inverse of g of x minus 2. Now, since this is a simple problem, leaving it in function notation is not a big deal, but sometimes when we're dealing with multiple exponents and multiple steps, it may get confusing and you may start assuming that we have variables and exponents when this truly represents the inverse of the function. So I always recommend just switching things in terms of x and y, but just to show you that you can still do it this way, let's continue on. All I have to do is add 2 to both sides, so to get that x plus 2 equals 1 over the inverse of g of x. And in order to solve for the inverse of g of x, since we have 1 over the inverse of g of x, we know that the inverse is going to be equal to 1 over x plus 2. If I were to take this and multiply to this side to get it out of the denominator, I would then need to take this entire quantity and divide by it, which would put it into a denominator. So our solution, number 10, is the inverse of g of x equals 1 over x plus 2. Moving on to number 11, I'm going to write this as y equals 2x cubed plus 3. What do we do first? We switch x and y. So we're going to have x equals 2 times y cubed plus 3. And then what do? We solve for y and put it back in function notation. So solving for y, we're going to start by subtracting 3. So we have x minus 3 equals 2 times y cubed. Next, think of reversing those order of operations. We'll deal with this exponent last, so we're going to divide by 2 next. So we have x minus 3 over 2 equals y cubed. And our last and final step is to take the cube root of both sides. So we have the cube root of x minus 3 over 2 equals the cube root of y cubed, which is y. And what exactly is y? We know that y is our inverse function. So the inverse of h of x. That inverse is equal to the cube root of x minus 3 over 2. Switching it out to function notation as that last and final step. Let's move on to number 12. In number 12, switching x and y at the start, we'll have that x is equal to negative 4y plus 1. Then we're going to solve for that y. So we'll simply subtract 1 from both sides to get that x minus 1 equals negative 4y. And then we'll divide by a negative 4. So we'll get that y is equal to x minus 1 over negative 4, or negative x minus 1 over 4. And there we have it. The inverse of g of x is equal to negative x minus 1 over 4. That's our solution in number 12. And if you're looking at the answer key, you may see that they've broken this fraction up into negative x over 4, or negative 1/4 x plus 1/4, or negative 1/4 x plus 1/4. Either is perfectly fine. Let's move on to number 13. In number 13, 7x plus 18 over 2, we're going to swap that x and y. So we're going to have x equals 7 times y plus 18 over 2. Next, solve for y. Once we solve for y, we just write it in function notation. So we're going to multiply both sides by 2 to get that 2x equals 7y plus 18. Then we'll subtract that 18 from both sides to that 2x minus 18 equals 7y. And then our last and final step, we just have to divide both sides by 7. So 2x minus 18 over 7 equals the inverse function of g of x. 14 seems pretty straightforward. What do? We switch our x and y. But in this case, since it is quite a simple problem, I'm just going to keep this in function notation. So I'm going to say that x equals the inverse of f of x plus 3. So you can see that I just switched x and this function, but when I switched it, I made sure to note that it's now the inverse function. That's what it represents. And you can see that all I need to do is subtract 3 from both sides to get that the inverse of f of x equals x minus 3. Let's move on to number 15. In number 15, f of x equals negative x plus 3. So for writing x equals negative y plus 3 and solving for y, I'll just subtract 3 from both sides. So I'll get x minus 3 equals negative y. And then I'll divide by negative 1 or multiply by negative 1 to get that negative x plus 3 equals y. But what really is y? Remember, when we swap those, we know that y is technically equal to the inverse of f of x. So rewriting this, we'll have that the inverse is equal to negative x plus 3. And that's our solution for number 15. Number 16 is also fairly straightforward. We're going to start by swapping f of x and x, but remember when we swap those, it's really the inverse function that we now have. So I'm going to have that x equals 4y, where y represents that inverse function. So all I have to do is divide both sides by 4 to get that the inverse of f of x equals x over 4. And that's my final solution for this set of directions. If you've been finding this video helpful so far, please feel free to give me a thumbs up. And if you can think of somebody else that'll find it useful, go ahead and share it with them as well. For now, let's continue on to our last set of directions. And for our last set of directions, it says to find the inverse of each function, then graph the function and its inverse. So let's go ahead and dive into number 17. For number 17, we have f of x equals -1 minus 1/5 x. Remember, when we swap x and y, we'll then solve for y. So we're going to have that x equals -1 minus 1/5 times y. Adding 1 to both sides, we'll get x plus 1 equals -1/5 times y, and then I'll multiply by a -5. When I multiply both sides by a -5, you'll see that my 1/5, that's negative, cancels out. So I'll get that y, which represents the inverse of f of x, equals -5 times x plus 1, which is -5x minus 5. So here we have the inverse of the function. Now we just need to graph both of them. And both of these are quite easy to graph since they are both linear equations. So starting with graphing our original function, I'll graph that in blue. We're going to have our intercept, if I was to plug in 0 for x, is a -1. And you can see our slope is -1/5. Rise over run. Every one I go down, I go 5 to the right. 1, 2, 3, 4, 5. 2 points will help us form that line, and I'll go ahead and connect that now. And I don't have a straight edge at the moment to work with, so I'm going to draw my line as best as I can. Now, the neat thing about inverses, like we learned up in that very first section, is x for one function is y for the other, and y for one function is x for the other. You can see here we have the point 5, -2. Well, I know in this function, I'm going to have the point -2, 5. So graphing that now in red, -2, 5 will be here. And we can confirm it if I were to plug in 0 for x to get my intercept. 0, -5 is going to be right here. And let's look at that rise over run. Well, our rise over run is simply -5, which I can write as 5 over -1. So if I were to go 5 up, 1, 2, 3, 4, 5, and 1 to the left, I'd be at this point here, which, look, here I have -1, 0, whereas here I had 0, -1. Switching those x and y's. And look at that line that we can now form, connecting those 3 points, even though we only needed 2 to form this linear equation. And there we have it, the function and its inverse both graphed. Moving on to number 18, we have g of x equals 1 over x minus 1. Let's start by solving for that inverse function. So I'm going to have x equals 1 over y minus 1. Solving for y, I'll start by multiplying both sides by y minus 1. So I'll get that y minus 1 times x equals 1. Then I'll divide both sides by x to get that y minus 1 equals 1 over x. And then finally, last but not least, add 1 to both sides to get that the inverse function of g of x equals 1 over x plus 1. Now we're going to graph these. And remember, what was x for one function becomes y for the other, and what was y for one function becomes x for the other. So for g of x, let's plug in some different values. Starting with plugging in 1 for x, I'm going to get 1 over 0, which is undefined. So I know that this is undefined, so my function is going to split. Whereas for here, I'm undefined at 0. So these functions are going to look fairly similar, but just with different asymptotes. So since I can't plug in 1 for x, let's try plugging in 0 for x. Plugging in 0, I'll get 1 over -1, which is a -1. So 0 for x results in -1 for y. Now I know for that function I have some asymptote, so I want to be sure that I capture both sides. So I'm going to plug in a few more negative numbers and a few positive numbers to the right of that positive one. So let's go ahead and plug in 2. Notice when I plug in 2 for x, I get 1 over 2 minus 1, which is 1. So I have the point 2, 1. Again, I know I have this undefined section here, so this is not going to connect like so. Let's keep working on this left-hand side. Let's plug in a -2. If I was to plug in a -2, I'd get -2 minus 1, which is a -3. 1 over -3 is a -1/3. So I have -2, -1/3, which is approximately here. And notice that as I keep going into the negatives, I'm just going to get smaller and smaller negative fractions. So this is going to go towards 0 as I go to the left. Continuing towards that +1, if I were to plug in, let's say, something like 1/2, 1/2 minus 1 is a -1/2. 1 over -1/2 is a -2. So 1/2, I'd be at -2. If I were to plug in 1/3, I would continue getting closer and closer to 1, but never touching it. So here we have a graph that looks something like this. Getting closer and closer to 1 and getting closer and closer to 0. And same here. It gets closer to 1 and closer to 0. Now graphing the inverse of this, my vertical asymptote is going to be when x is 0, and my horizontal asymptote is going to be that +1. So this function is going to look like so. The inverse of the function. Again, how you can graph this is by picking a few points of the function that we've already graphed and swapping those x and y values, or recognizing different horizontal and vertical asymptotes among the graph and graphing that way as well. But as you can see, in our original function, we had the point 2, 1, and in my inverse function, I have the point 1, 2. In my original function, I have the point 0, -1, and in my inverse function, I have the point -1, 0. So you can see those values are just swapped. Let's move on to number 19. Now number 19, we have f of x equals -2x cubed plus 1. Solving for y, once I switch those variables, we have x equals -2 times y cubed plus 1. Start by subtracting 1 from both sides, and that's going to equal -2 times y cubed. Then I'll divide both sides by -2, which I don't necessarily want this -2 in my denominator, so I'll write this as -x plus 1 over a +2 equals y cubed. Taking the cube root of both sides, I'll get that the cube root of -x plus 1 over 2 equals the inverse of f of x. Now this one is going to be a bit tricky to graph, so let's focus on graphing this original and then just swapping the values. So, starting off with f of x, let's plug in 0 for x. Plugging in 0 for x, -2 times 0 is 0, plus 1 is just 1. So I'll have 0, 1 in my original, and then in my inverse, I'll have 1, 0. Now let's plug in, let's say 1. Plugging in 1 for x cubed, I'll get -2 times 1 plus 1, so that's going to result in a -1. So I'll have 1, -1, whereas in my inverse function, I'll have -1, 1. Now let's try to find something in between these. Let's try 1/2. If we plugged in 1/2, we're going to get -2 times 1/2 cubed, which will result in 1/8, plus 1. -2 over 8 is -1/4, plus 1 is going to be a +3/4. And again, that's for when we plugged in 1/2. That resulted in a -1/4 plus 1, which was 3/4. So finding 1/2 and then marking 3/4, or for the inverse, finding 3/4 and marking 1/2. So you can kind of see that curve along the red and that curve along the blue, our original function versus our other function. Now let's go ahead and plug in, let's do a -1. Plugging in -1, -1 cubed is -1, -1 times -2 is a +2, 2 plus 1 is 3. So when I'm at -1 for my original function, I'm at a positive 3. Switching those, when I'm at a positive 3 for my inverse function, I'm at a negative 1. And just to further solidify these curves, let's choose another number like 2. If I was to plug in 2, 2 cubed is 8. 8 times negative 2 is a negative 16, plus 1 results in a negative 15. So when I'm at 2, I'm at negative 15, which is all the way somewhere down here. So I know I'm not even ever going to reach this 2. So when I'm at 2, I'm at negative 15, which is completely off my graph. So I'm never even going to reach 2 on this graph. So I know that my function is going to go down towards that 2. So if I were to plug in negative 15 into my inverse, I would get a positive 2. So you can see that I'm never going to reach this 2 on this graph. So my curve is going to look something like this. And negative 2 would be the same concept. If I plugged in a negative 2, it's going to go towards that positive 15. So my original function is going to look like this, because we're never going to quite reach that negative 2. And same for here. And then when we switch that, well, we're never going to quite reach the negative 2 here along our y. So we're going to draw it like such. And there we have it. The inverse functions graphed and solved for number 19. This one was a bit tricky, but feel free to get a more detailed graph using some graphing utilities. For now, let's move on to our last and final problem, number 20. For number 20, we have g of x equals negative x minus 5 all over 3. Let's solve for the inverse of g of x. So we're going to have that x equals negative y minus 5 over 3. Start by multiplying both sides by 3 to get that 3x equals negative y minus 5. Go ahead and add that 5 to both sides to get that 3x plus 5 equals a negative y. And last but not least, either multiply or divide by a negative 1 to get that negative 3x minus 5 equals a positive y. But what exactly is y? Y is our inverse of g of x. Now, we're dealing with two linear equations, so let's go ahead and start by graphing the inverse function, since that slope's a little bit easier to see. So when we plug in 0 for x, we're going to get negative 5 for y. So switching that for our original function, that means when we plug in negative 5 for x, we're going to get 0 for y. So this point here. Now let's plug in another number. Let's say we plug in a negative 1 for x. Or let's go ahead and use that slope. We know that slope is negative 3. So for rise over run, if we were to go up 3, 1, 2, 3, we need to go to the left 1 to get that negative 3 for our slope. So we're at the point negative 1, negative 2. That means in our original function, when we're at negative 2, we're at a negative 1. And you can see the slope here is that negative 1/3. Rise over run, negative 1 over 3, 1 down, 3 over. We do indeed get that same point. And since they're both linear equations, 2 points make a line, so just go ahead and draw those lines. And you can see if you're to use a straight edge, you'll get more accurate results, but let's check closer to those points. I have the point 1, negative 2 here, and here I have the point negative 2, 1. Again, confirming that these are inverse functions. If you have any questions, please feel free to leave a comment below, and I or one of your peers will get back to you as soon as we can. But as always, to show your support, don't forget to like, subscribe, and share. Happy learning!